Welcome to a new microeconomics video lesson in this blog dedicated to game theory. With this video, we will start the part dedicated to dynamic games. On this occasion, we will talk about the basic concepts necessary to understand a dynamic game, and later on in other videos, we will discuss how to find the solution in such games. A dynamic game in general is any non-static game. Therefore, these games are characterized by meeting at least one of these two properties. First, at least one of the players makes more than one decision throughout the game, or secondly, not all players make their decisions simultaneously. In order to predict the behavior of players in any dynamic game, we first require certain information, that is, the description of the game. So far, we have only seen how to describe a static game in a strategic or normal way. However, apart from the normal way, any game, whether static or dynamic, can also be described in an extensive way. To describe a game in an extensive way, as we saw in previous videos, we need to describe graphically or with words its decision tree or game tree. Among other things, a game tree consists of, firstly, endpoints called nodes, then vectors of numbers, also arrows or lines that point from one node to another or to a vector, as we call also branches, and finally labels for each node and each arrow. Each node represents a different situation in which a player must choose. Each arrow represents a different alternative or a strategy for each player. Vectors are used to represent the payoffs or utilities at each of the possible ends or final results of the game. And finally, the labels of each node indicates which player is choosing at that node, and the labels of each arrow contains the name of the strategies. In every decision tree, the following must always be true. Firstly, there is a single node called the starting or initial node, to which no arrow points. It represents the beginning of the game. Each of the remaining nodes and all vectors has an only arrow pointing to it. All of the above implies that there is a unique path composed of arrows from the starting node to any of the remaining nodes or vectors. For this reason, we refer to it as a decision tree. Each of the paths is like a branch of a tree. For example, the decision tree shown represents in an extensive way the following dynamic game with 3 players, 1, 2, and 3. At the starting node, player 1 moves first, choosing between continuing the game, C1, or ending it, E1. If the latter, players 1, 2, and 3 receive respectively utilities of 1, 8, and 8. If 1 continues, then player 2 chooses between continuing a game, C2, or ending the game, E2, leading to a payoff vector of 2, 0, and 8. If player 2 continues, finally player 3 can choose between the payoff vectors 2, 1, and 5, or 4, 3, 4. There is one last point about decision or game trees. How can we represent situations in which 2 or more players choose in a simultaneous way with game trees? For example, without knowing what the others chose previously. For example, how can we represent the game rock, paper, scissors in which 2 players simultaneously choose among these 3 actions? The key here is the dashed line connecting 3 nodes, labeled 2, in the graph. The dashed line indicates that player 2, when making a move at any of those nodes, doesn't know exactly which node they are at. In other words, they don't know what player 1 chooses. Note that if we change the 1 level at the initial node to number 2 and the 2 level to the 1, the new game tree would also represent rock, paper, scissors. In other words, when we represent simultaneously made decisions, the order in which we arrange the node is completely irrelevant. The previous explanation allows us to introduce the concept of an information set. Information set is any set of nodes of a single player such that if the player moves at one of them, they do not know whether they are at that node or at one of the other nodes. Note that if the set contains only one node, obviously there is no such problem. Depending on the game, there may be information sets that contain one, two, or more nodes. For example, if rock, paper, scissors is played simultaneously, each player has only one information set. But if the game is played sequentially, player 2 has 3 information sets and player 1 has only one. Let's now introduce our new concept related to dynamic games. For this, consider a game in an extensive way with at least one single node information set. Let's call the corresponding node as n, and note it must be different from the starting node. Now consider for every node n prime that follows n, the information set to which n prime belongs. If all the nodes included in that set also follow n, we can say that the part of the game tree that comes after n is or will be a subgame. For example, in the ultimatum minigame that is represented in the following graph, there will be two different subgames. The first one after the player 1 choosing O1, and the second one after the player 1 has chosen C2. In static games that we show in previous videos, a strategy was simply an action. In dynamic games, on the other hand, a strategy is generally something more complex. In particular, a strategy of any player in dynamic games will be a list or vector of actions, one for each information set the player has, with each action corresponding to a different information set. That is, a strategy for any player must indicate how this player would move in every potential decision for this player in the game, regardless of whether that point is reached or not in the game. So these are exhaustive instructions for every likely decision for each player. For example, what are the likely strategies for the players in the ultimatum minigame shown in the tree in this image? Okay, player 2 has two information sets, and at each one there are two likely moves, A and R. Therefore, this player has 4 likely strategies, and as for player 1, they only have one information set. Therefore, any strategy they choose consists of just one action. There are 2 likely strategies, O1 and O2. Once the strategies of the players are shown, and as long as the number of strategies is finite, we can show the matrician or a normal way of a dynamic two-player game using also a payoff matrix. Note that each player must have as many rows or columns in this matrix as they have strategies. Each cell should show the payoffs to each player if the players behave according to the corresponding strategies. For example, the payoff matrix for the ultimatum minigame is as follows, with player 1 on the rows and player 2 on the columns, although it could be done in the opposite way. For example, in the cell O1, R1, A2, the payoffs are 0, 0. because if player 1 chooses O1 and player 2 plays according to the strategy profile A1 and A2, then each player gets a payoff of 0. One offers O1 and player 2 rejects it. Why are then two likely ways to describe a game? Why not just using only one? Note that the main difference between these two ways is that the strategic way or normal way provides, in general, less information about the game, while the extensive way adds information about, on one side, the order in which the players make the different decisions, and in the other side, what each player knows at the moment of making a decision about how the other players have behaved so far. Most theorists think that the information in the normal way will be enough to predict behaviors in static ways, which is why we didn't discuss the game trees in the previous videos. However, in dynamic games, many theorists think the opposite. Therefore, they prefer to use the extensive or game trees, although this remains open to debate.